Right now, somewhere in a heavily cooled laboratory, a machine that could change the future of humanity is losing its mind. Not metaphorically, not slowly. It is forgetting in real time everything it was just thinking. And it is doing this within millionths of a second. That is the brutal, terrifying reality of quantum computing in 2025, and nobody is talking about it the way they should be. You have been told that quantum computers are going to revolutionize medicine, break encryption, simulate the universe, and solve problems that classical computers could not crack in a billion years. And that part is true. But there's a dark side to this story that researchers are fighting every single day, and it has a name. It is called decoherence. And if humanity cannot figure out how to stop it, every single promise quantum computing has ever made will remain just that, a promise. So today, we are going in deep. We are going to talk about what decoherence actually is, why it happens, how scientists are desperately trying to fight it, why Google just made a chip that shocked the world, and why this invisible enemy could be the single greatest obstacle standing between us and a technological revolution. Stay with me, because this is the kind of science that genuinely keeps physicists up at night. Like and subscribe, because what you are about to hear will completely change how you think about the future of computers. Let us start at the very beginning, because to understand why forgetting is terrifying in a quantum computer, you first need to understand what makes a quantum computer different from the one sitting on your desk or in your pocket. A regular computer works with bits. Each bit is either a 0 or a 1. That is, it. That is the whole language of every phone, laptop, and server on the planet. Simple, clean, and reliable. A quantum computer works with something called qubits. And a qubit is not just a 0 or a 1. It can be both at the same time. This is called superposition. It sounds like science fiction, but it is real, proven, and foundational to quantum physics. A qubit exists in a cloud of probability, partly 0, partly 1, and every combination in between, until the moment you actually measure it. At that point, it collapses into a definite answer. That collapse is where the magic happens. Quantum computers can explore millions of possible solutions simultaneously and find the right answer. In a fraction of the time a classical computer would need. The second quantum trick is called entanglement. When two qubits become entangled, the state of one instantly influences the state of the other, no matter how far apart they are. Einstein called this spooky action at a distance, and he was not wrong. It is strange, it is counterintuitive, and it is extraordinarily powerful. Together, superposition and entanglement are what give quantum computers their almost supernatural computing power. But here is the problem, and this is the part that most YouTube channels and tech articles gloss over. These quantum states are insanely, almost impossibly fragile. The moment a qubit interacts with literally anything in its environment, a stray photon, a tiny vibration, a random electromagnetic fluctuation, even the heat radiating off a nearby wire, its quantum state collapses. That delicate cloud of probability that makes it powerful gets destroyed. The qubit forgets what it was doing. It loses its quantum identity and becomes just a boring classical bit. This process is called decoherence, and it is, without exaggeration, the central existential threat to quantum computing. Like and subscribe, because what is coming next will genuinely shock you. To give you a sense of how brutal decoherence is, consider this. The coherence time of a qubit, meaning the window during which it actually behaves as a quantum object before it forgets everything, ranges from nanoseconds to, if you are lucky and extremely careful, around a few hundred microseconds in the best superconducting qubit systems available today. A microsecond is 1/millionth of a second. Even the most sophisticated superconducting qubits built by companies like Google and IBM typically maintain coherence for somewhere between 20 and 100 microseconds under standard conditions. Trapped ion qubits, which are physically different and harder to operate, can hold their quantum state for seconds or even minutes, but they come with an entirely different set of problems. The point I has this. The window in which a quantum computer can actually do useful work before its qubits start forgetting is terrifyingly small. Researchers have to perform every calculation, every error check, and every correction inside that tiny window before the whole system degrades into noise. That is like trying to solve a complex math problem while someone is constantly turning your brain off and on. Like and subscribe, because the real horror story is just getting started. Now, you might be wondering, why not just build better qubits? Why not just make them stronger so they do not decohere? And that is exactly the question scientists have been wrestling with for decades. The answer is devastatingly complicated. Qubits are not decoherent because of poor engineering. They are decoherent because of physics itself. Quantum mechanics demands that a quantum system interacting with its environment will lose its coherence. There is no material, no design, no engineering trick that can fully prevent this. You can slow it down, you can delay it. But in theory, according to the laws of physics, all physical systems interact with their environment to some degree and some amount of. Decoherence is inevitable. The best researchers can do is isolate the qubits as much as humanly, or physically possible. This is why superconducting quantum computers, including the machines built by Google, IBM, and others, have to be cooled to temperatures colder than outer space. We are talking about roughly 15 millikelvins, which is colder than the cosmic microwave. Background radiation that fills the universe. The machines are basically refrigerators the size of chandeliers, hanging in heavily shielded rooms, vibrating at near absolute zero. And even then, even in that extreme environment, the qubits still forget. They still decohere. Still, within hundreds of microseconds, the quantum information bleeds away into the environment. The physics does not care how cold you made the room. And it gets worse. Even when you solve one source of decoherence, another one appears. Researchers in 2024 discovered that the vibrations from the very cooling systems used to keep the qubits cold were themselves causing decoherence bursts. The pulse tube coolers, the machines that chill the qubits, shake the chip ever so slightly, and that tiny mechanical vibration disturbs microscopic defects called two-level systems, or TLS, embedded in the chip's materials. Those defects then interact with the qubits and cause correlated errors, meaning multiple qubits fail at the same time. It is a cruel, almost comical irony. The machine you use to protect the qubits is simultaneously destroying them. Like and subscribe, because quantum computing's biggest enemy might be its own hardware. This is where the story gets truly terrifying from a practical standpoint. Because decoherence does not just mean individual qubits make random mistakes. It means that complex quantum calculations, the kind that would take a classical supercomputer longer than the age of the universe to complete, can completely fall apart before they even finish running. Every quantum algorithm that promises to revolutionize drug discovery, materials science, financial modeling, or artificial intelligence requires qubits to maintain their coherence for long enough to complete meaningful calculations. And right now, in 2025, even the most advanced machines in the world cannot reliably do that for complex, long-running programs. The gap between what quantum computers can theoretically do and what they can actually sustain before decoherence destroys the computation is enormous. It is the single biggest reason why quantum computers, despite decades of hype and billions of dollars in investment, have not yet solved a single real-world problem that a classical computer could not solve faster and more cheaply. Like and subscribe, because that sentence right there is what the tech industry does not want you to know. This brings us to quantum error correction, which is humanity's best response to the decoherence problem. And while it is a genuine breakthrough in theory, the practical cost of implementing it is almost mind-bending. Here's the core idea. You cannot directly observe a qubit without collapsing its quantum state, so you cannot just check whether it has made an error the way you can with a classical bit. Instead, researchers spread the quantum information from a single logical qubit across many physical qubits. These extra qubits act as a safety net. They allow the system to detect and correct errors without directly measuring, and thus destroying, the quantum information. The concept works on paper. The problem is the overhead. To protect one single logical qubit, well enough to run complex algorithms reliably, you may need hundreds or even thousands of physical qubits working in parallel just for error correction. Some estimates suggest that cracking modern RSA encryption using a quantum computer would require around 20 million noisy physical qubits to produce enough reliable logical qubits to complete the task. As of 2025, the most advanced machines have a few hundred to a few thousand qubits. That gap is staggering. Like and subscribe, because this number is going to haunt the cybersecurity world for the next decade. The reason error correction requires so many physical qubits is directly because of decoherence. Each physical qubit is constantly fighting against decoherence, making errors at a certain rate. The error correction scheme has to run fast enough and accurately enough to catch those errors before they cascade through the system. If the error rate of the physical qubits is above a certain threshold, called the fault-tolerance threshold, then the error correction process itself introduces more errors than it fixes. You're trying to clean up a mess with a dirty mop. Only when the error rates per qubit drop below that critical threshold does error correction actually start helping. Researchers at Google made a genuinely historic breakthrough on this front in December 2024 with their Willow chip. Their 105 qubit superconducting quantum processor demonstrated for the first time that as they added more qubits and scaled up the error correction grid, the error rate actually decreased exponentially rather than growing. This was a theoretical prediction from quantum computing's earliest days, but it had never been cleanly demonstrated in hardware before. Willow also performed a benchmark. computation in under 5 minutes that would take one of today's fastest classical supercomputers 10 to the power of 25 years, a number so large it dwarfs the age of the universe by an almost incomprehensible margin. Like and subscribe, because Google just proved something scientists have been waiting 30 years to see. But, and this is critical, even Google's Willow chip is nowhere near being able to crack encryption or solve practical large-scale problems. The demonstration was a carefully designed benchmark, not a general-purpose computation. The chip still suffers from decoherence. The qubits still forget. The error rates are better, but they are still far too high to run the kind of deep, complex quantum circuits that would be needed for transformative real-world applications. Google's team has been clear about this. Willow is a milestone on the road, not the destination. The physics of decoherence has not been defeated. It has merely been slightly pushed back. And pushing it back further, all the way to fault-tolerant quantum computing, will require scaling from 105 qubits to potentially millions of qubits, each one carefully isolated, error-corrected, and maintained at temperatures colder than space. That engineering challenge is unlike anything humanity has ever attempted. Let us now zoom out and talk about why any of this matters to people who are not quantum physicists, because the implications of decoherence extend far beyond academic research labs. The most alarming consequence of the quantum decoherence problem playing out in a particular way involves cybersecurity and national security. Here is what you need to understand. Almost all of the encryption that protects your bank accounts, your messages, your medical records, and your government's most sensitive communications relies on a mathematical problem, factoring very large G numbers, that classical computers are essentially unable to solve in any practical time frame. RSA encryption, which is the backbone of most secure internet communications, is safe precisely because factoring a 2048-bit number would take a classical computer longer than the lifetime of the universe to crack. A fault-tolerant quantum computer running Shor's algorithm could theoretically crack that same encryption in hours. Like and subscribe, because what you just heard is why intelligence agencies around the world are already panicking. The terrifying thing is not just that quantum computers will eventually threaten encryption. The terrifying thing is that adversaries, nation-states, sophisticated criminal organizations, and intelligence agencies are already stealing encrypted data today to decrypt it later once powerful enough quantum computers exist. This strategy is called Harvest Now, Decrypt Later. Your encrypted medical records, financial data, government communications, and private messages could already be sitting on a server somewhere, waiting for the day a fault-tolerant quantum computer powerful enough to crack them finally comes online. The NSA has already recognized this threat. Under its CNSA 2.0 directive, the United States has mandated that national security systems begin migrating to quantum-resistant cryptographic algorithms with full compliance required by 2035. The problem is that cryptographic transitions historically take 10 to 20 years to complete across global digital infrastructure. And we are already running behind. Like and subscribe, because the data being stolen right now could be your own. NIST, the National Institute of Standards and Technology, finalized its first post-quantum cryptographic standards in August 2024, a milestone years in the making. These new algorithms are designed to be resistant to both classical and quantum attacks, but awareness of this issue in the private sector is still dangerously low. Banks, hospitals, telecommunications companies, and cloud providers are running on encryption that a sufficiently advanced quantum computer will be able to break. And while decoherence is currently their biggest enemy, keeping those quantum computers from reaching the power level needed to crack encryption, it is not a permanent barrier. Every month, every year, the coherence times improve. The error rates drop, the qubit counts rise, the race is on, and most of the world is not even watching. Now let us talk about where the science is going, because despite everything we have covered, there are genuine, astonishing reasons for optimism if the physics can be tamed. Researchers around the world are pursuing multiple radically different approaches to defeating decoherence. One of the most exciting is topological qubits. Unlike superconducting or trapped ion qubits, topological qubits encode quantum information in a fundamentally different way, using exotic quantum states called anyons whose properties depend on the global structure of the system, not on any local physical detail. Because the information is stored non-locally, it is inherently more resistant to local noise and decoherence. Microsoft has been pursuing this approach for years. As of 2025, topological qubits remain largely experimental, but the theoretical advantage they offer is real. If they can be made to work reliably, they could sidestep large parts of the decoherence problem in a way that current qubit types simply cannot. Another approach gaining momentum is cat qubits, which exploit a clever asymmetry in quantum noise to make one type of error, bit flip errors, exponentially rare, even while phase flip errors remain. This reduces the overall error correction overhead dramatically because you only have to protect against one dominant type of error instead of both. French startup Alice and Bob has been pioneering this approach, and coherence records for cat qubit bit flip times have broken through to over 0.1 seconds, an enormous improvement over standard superconducting qubits. In 2025, adaptive control systems demonstrated a 10-fold reduction in noise by adjusting qubit parameters in real time based on feedback from the environment. IBM's late 2024 Heron R2 processor brought significant improvements in coherence, gate fidelity, and computational efficiency with 156 qubits. In a groundbreaking paper published in Nature Physics in early 2026 by researchers at the University of Tokyo, introduced a new fault-tolerant protocol that tackles both the number of physical qubits needed and the time required to perform logical operations simultaneously, something that had previously proved almost impossible to do together. Like and subscribe, because science is fighting back against decoherence in ways that would have seemed like science fiction just 5 years ago. Quera Computing, working with Harvard and Yale, published work in Nature in September 2025, introducing a framework called algorithmic fault tolerance, which drastically reduces the time overhead of error correction in quantum algorithms. Neutral atom quantum computers, where individual atoms are held in place by laser beams called optical tweezers, have emerged as a genuinely competitive alternative to superconducting systems, with a key advantage being that atoms can be rearranged mid-computation to allow more flexible and efficient error correction. A 6,100 qubit neutral atom quantum array was demonstrated at Caltech. In 2025, the largest reported quantum system to date, yet even that machine remains fundamentally limited by coherence times and error rates. The headline numbers are improving. The physics is relentlessly, stubbornly hard. The enemy, Decoherence, has not surrendered. It has merely retreated slightly. What does all of this mean for you right now in practical terms? It means we are at one of the most genuinely strange and consequential moments in the history of technology. The machines exist. The algorithms are written. The theory says quantum computers should be able to transform medicine, chemistry, artificial intelligence, and cryptography in ways we can barely imagine. And yet, the universe itself seems to be pushing back. The laws of quantum mechanics create a machine that is also its own worst enemy. Every qubit that gains the power to compute simultaneously forgets within a fraction of a heartbeat. Every calculation that could crack an encryption key or discover a life-saving molecule is in a constant race against the clock of decoherence. Scientists are fighting G-physics with physics, using topological protection, error-correcting codes, laser cooling, electromagnetic shielding, and adaptive feedback systems to squeeze every extra microsecond of coherence out of materials and geometries that operate at the extreme edges of what matter can do. The timeline for when a truly fault-tolerant large-scale quantum computer will exist is genuinely uncertain. Optimistic estimates from major research groups suggest useful fault-tolerant quantum computation could arrive sometime in the 2030s. Other researchers are more cautious, pointing out that the gap between current qubit counts and the millions needed for practical fault tolerance is not just engineering, it is a fundamental scientific challenge that could take far longer to crack. What is not uncertain is the direction. Every year the coherence times grow, every year the error rates drop, every year the qubit counts increase. Google's Willow chip proved that the underlying theory is correct, and that error rates can decrease the system's scale, not just stay the same or worsen. That was a foundational proof of concept that the entire field had been working toward for decades. But what terrifies researchers most is not that quantum computers will fail. It is that they will succeed. Not fully, not fault-tolerantly, but just enough. Just enough to crack some early encryption systems before the world has fully migrated to quantum-resistant algorithms. Just enough to give a hostile nation-state or criminal organization a window of advantage that could reshape geopolitics, drain financial systems, or expose classified communications. The middle ground, a quantum computer powerful enough to cause a harm but too decoherent to be controlled reliably, is in some ways the most dangerous outcome. And based on the trajectory of the science, that middle ground may arrive before we are ready for it. Quantum computing is not a distant science fiction concept. It is not a promise for your grandchildren's generation. It is happening right now in laboratories cooled to near absolute zero on chips built atom by atom, in research papers that are rewriting what physics says is possible. The machines are forgetting, the scientists are fighting, and the entire future of digital civilization, your encryption, your privacy, your medical data, your financial system, is caught in the crossfire of a battle between human ingenuity and the fundamental laws of the universe. Like and subscribe, because staying informed about this technology is not optional anymore. It is how you protect yourself in a world that is changing faster than most people realize. The next time someone tells you quantum computers are just hype, remember this. The hype is not about whether the machines work. It is about whether we can teach them to remember. Right now, they are still forgetting. But the race to fix that, the race to preserve a quantum state long enough to change the world, is the most important scientific competition of the 21st century.